Next, I'm going to go and give another example that you haven't seen before. But first, I just want to give people an opportunity to ask questions. Okay. And there's also, there's also a greedy algorithms problem on your homework assignment. But let's try a problem that is always a favorite of mine. So buying commodities. So the idea is, that I have a limited budget. Say I have like $100 and I'm interested in buying, let's say, some grain. And so maybe like a bushel of corn costs $30 and a bushel of oats costs $40 and a bushel of rice. I don't actually know how much a bushel is, but I think usually grains are always measured out in bushels. A bushel of rice is only $25. A bushel of wheat, we'll say a bushel of wheat is, we'll say, I don't know, maybe wheat's expensive right now. 45, and then a bushel of oats, wheat, rice, corn, barley. Okay, so we'll say something like this. Again, I'm just making up these numbers, but I have a limited budget to go and buy some grain. And each, there's a cost associated with each of these bushels, but also each grain has a value to me. So I like some grains more than others. So we can say that this is the, let's say that a bushel of corn has 3 value to me. A bushel of oats has 8 value to me. A bushel of rice has, let's say, 5 value to me. A bushel of wheat has like 4 value to me, and a bushel of barley has 6 value to me. So again, I'm just making up these numbers, but the goal is that each grain has value to me. I want as much grain, I want as much value as possible while staying within my budget. Okay, so it turns out, let me go pull this down. So it turns out that this is a famously hard problem. This is a famously hard problem if you can't split, if you can't buy a fraction of a bushel. Then you basically need to brute force. Okay, so this problem, I said at the top here that this is this is going and buying divisible commodities. What I mean by divisible commodities is like, it makes sense to buy half a bushel of corn. It doesn't make sense to go and buy like half of a Toyota Camry. it doesn't make sense to go and buy like half of a banana or half a sofa. So in a lot of cases, you can't go and break down items into pieces. And then this idea of staying within your budget and maximizing value, finding the absolute best way to get value out of your budget is actually a really hard problem for computers to solve if you can't split up an item into pieces. But if I can buy any fraction of a bushel of corn, like half a bushel or 2/3 of a bushel, then this actually becomes an easy problem that can be solved with a greedy algorithm. So let's go and use our greedy algorithm approach. So this is, I guess, first of all, does this problem make sense? The problem, right, you can see intuitively here that like oats are giving me a lot of value, and so like probably I want my solution to have a bunch of oats. So wheat is expensive and is like wheat costs more than oats, and it's giving me less value than oats. So probably I'm less interested in getting wheat. I probably don't want to be filling up my spending my money on wheat if there's oats available to buy. So
I have a question.
Yeah.
This like kind of reminds me of in linear algebra. I can't tell you like what part of it was specifically, but probably like a few months ago, we were kind of doing a similar thing where it was like you would have like different, I think we used like a lot of like nutrient, like ingredient kind of examples, but it was like each one had like a certain amount of like whatever value that you wanted, but like also like fat or whatever. And you were trying to find like the maximum, like, or like a given ratio. Is this like related somehow to linear algebra or?
Yeah. So the solution that we are going to pose here today, the solution that we're going to pose here today is we're not going to use vectors and matrices right now for this class. On the other hand, you can definitely think of this as a linear algebra problem. There's a if we have a solution and the solution is like, at the end of the day, my solution is going to be how much corn do I buy? How many oats do I buy? How much rice do I buy? You can think of your solution as a vector, and then there's a transformation on that vector that tells you there's a transformation on that vector that tells you how valuable a particular vector is, and our budget is going and putting constraints on that vector. So like, yeah, this like 100% one way to solve this problem is to cast this as like, basically our budget is telling us that there's a linear transformation, and the cost transformation on this vector cannot be more than a certain amount. And given that like linear constraint, we're interested in going and maximizing the value function applied to the vector. So yeah, so like this can all be linear algebra, but the solution that I'm going to put forward today is not going to be a linear algebra type solution. Again, many cases, like, you know, there's a lot of problems where if you squint at the problem enough, it's like, oh, this is just vectors and matrices. I have a toolbox of algorithms that work for vectors and matrices. Let me go and use that. So that's not what we're going to come up with today, but it's a good solution approach. And it's like, yes, it is a great observation that like, hey, this is just vectors and dot products and linear transformations.
Okay, thank you.
Any other, let's see, was there any other questions here? Yeah, so again, regardless of whether or not you pose this as a a linear algebra problem or whether you pose this as a like combinatorics problem, in either case, yeah, this is you're going to necessarily end up with like fractions in your solution. Doing this without fractions is hard, and like linear algebra won't save you. I don't know if that makes sense or not, but yeah, you would definitely have, if you go and solve this using linear algebra, you'll definitely get fractional bushels. But that's 100% fine to be getting fractional bushels because like a bushel of corn is easily divided into pieces. Most sellers of corn will sell me it in increments less than a bushel. So let me go and apply this greedy paradigm. So the first question when we apply this greedy paradigm, no. Let's see. So the first thing is we have to say, what are the repeated choices that we're making? And our repeated choices are, so we repeatedly choose, to purchase some amount of some grain. Some grain, or in general, some commodity. Some commodity or good. Okay, so first of all, like the way I'm going to build up a solution is I'm going to say, first of all, we're going to go use like I'm going to buy some amount of corn, and then I say I'm going to buy some amount of barley, and then I say I'm going to buy some amount of rice. So at every moment in time, I'm choosing to spend some amount of money on some fraction of a bushel of grain. So then what's feasible or allowed is, so in this problem, there's only 1 bushel available of each grain. So I can make any choice as long as it doesn't involve buying more grain than is for sale. I should note, like here in this example problem, I'll put 1 bushel of corn, 1 bushel of oats, 1 bushel of rice. If the market that I'm going to has 8 bushels of wheat, like that's perfectly fine. This all still works with any number of bushels available in the marketplace. So I've got some limitation though on how much product is available. So so the first issue is why can I not get these numbers to work? So I don't involve buying more grain that is for sale, and I don't spend more than my budget. So I can't go and make a choice that involves buying more grain than is available at the market, and I can't make a choice that involves spending more than my $100. So those are my feasible choices. And then the final piece of this is, well, what is the goodness of each possible choice? And the like, the goodness of a choice is how much the goodness of a choice is just the, let's see, is the amount that I buy times the value. So, for example, at the start, buying all of the buying all of the available, like buying all of the available oats has a value of 8. All of the available oats is feasible and has a value of 8. So wait, this is the actually I realize I messed up here. Actually, I think I want to look at the goodness of a choice. Let's say the goodness of a choice is actually the value divided by the price. I think this is actually the right greedy algorithm. So, for example, at the start, for example, using the above numbers. So let me go and grab this again. So this is the value per cost is going to be 3 divided by 30, which is 1/10. A bushel of oats, so buying, let's do this. Buying a bushel of oats is 1/5, because it's 8/40 is like 1/5, which is, I can write this as 2/10. Then buying 1 bushel of rice is, so this is like 5/25. This is also 2/10. 5/25 is 2/10. Buying 1 bushel of wheat. So this is 4/4.5 is like, wait, 4/45. This is like 8/90. This is a little bit ugly. So this is in particular less than this is less than 1/10. You can go and like enter this into a calculator somewhere if you don't believe me. And then similarly, buying 1 bushel of barley is 6/50. 6/50. So 6/50 is going to be 12/100, which is like 1.2/10. So yeah, so here you can see that buying rice and buying oats gives me more value for my dollar. I have a limited number of dollars, so the greedy approach is pick the commodity with the highest value per dollar, then buy as much as I can. So basically, first buy all of the oats for how much does buying all of the oats cost? All of the oats is 40. So buy all of the oats for $40. Next, what is the thing that is next good? Oats are wonderful. What are the things that are next good after oats is going to be rice. So next, buy all of the rice for $25. So this is now $60 left. This is now 60 minus 25 is $35 left. So then what is the best good that I have? I've bought all the oats. I've bought all the rice. The next good is going to be barley. So barley was 6 value for $50. I don't have $50. So next best is barley. I can't buy all of it, but I want to spend all of my remaining money on barley. So this is, I can buy 35 out of 50, which is 7/10 of a bushel. So I end up with 1 bushel of oats, 1 bushel of rice, and 7/10 of a bushel of barley. Okay, so is there any question about this greedy approach? My greedy approach of figure out the value per dollar of each good. If I figure out the value per dollar of each good and then buy as much of the good as I can, buy as much of whatever the best like bang for my buck is, buy it until it runs out, and then go to the next item on my shopping list. Are there questions about how this works?
I don't have a question about how it works, but I just wanted to confirm that in general, and like this one too, like greedy algorithms don't always give us the correct answer, right?
Yeah, so I'd like to talk about that for this particular problem. So it is the case for each of the 3 problems that I've put in today's example. The greedy algorithm is giving us the best possible answer. And we discussed in class early on why selection sort works. I think you should be able to convince yourself that selection sort works for a greedy sort. Kruskal's algorithm, it is less obvious that it works, but there's an explanation in the textbook of why Kruskal's algorithm always gives you the minimum spanning tree. But for this greedy algorithm that I came up with here, there is no reason off the top of your head, there is no reason that you should believe that this algorithm actually works. So the last thing that I wanted to do today was give you an explanation of why this algorithm actually works. Why is it the case that always buying the thing with the, here is the value per dollar, right? Always buying the thing that gives me the most value per dollar. Why is that the right answer? Why does that actually work? I mean, it seems kind of intuitive that if I can get a great deal on oats, then like, yeah, buying a lot of oats kind of makes sense. But arguing that this is correct takes a little bit of thought. So let me just check and see in the chat. Is there, no, there weren't questions on this. So, and I will note here that if you're not allowed to buy 7/10 of a bushel of barley, what makes this problem hard if you're not allowed to buy 7/10 of a bushel of barley, if you don't have any good use for your $35 that are left, because you have to buy like if you're in some weird market where you have to buy by the bushel and nobody will split a bushel into pieces for you, then all of a sudden this greedy algorithm fails, because if I get left with like $35 or $15 left at the end, I may then second guess all of the choices that I made up until this point. It's like, oh, I'm sitting with $35. There's nothing I can do that is good with this $35. Maybe I shouldn't have bought the last thing. Maybe if I had more money, I could go and actually use my final dollars more efficiently. So intuitively, this approach very much depends on the fact that I can buy fractional bushels. And so I never have to worry about having wasted dollars left at the end. Okay. So then let's finish with a very simple, not a very simple, but an overview of why does this work? And so my general approach for correctness of greedy algorithms is I often, again, there's a bunch of ways to make these arguments. I often find what is most clear for me personally, and again, this is only me. There are multiple ways to make these arguments, but I like the approach of assume the algorithm doesn't work and argue this is impossible. Right. So I want to yeah. So this is often called like proof by contradiction, or arguing the contrapositive. If you, contrapositive is a, I think I'm not actually going to go into contrapositive here unless if somebody wants to have a discussion of contrapositive at the end, I'm happy to have a discussion of contrapositive. But the idea here is to show that to say, okay, if this algorithm doesn't work, if suppose someone comes to me with an alternative solution that is more value for my budget than what the algorithm produces. I want to argue that they are full of crap, right? If someone comes to me and claims they have an alternative solution, so this is like, so if we suppose my friend Alice comes to me and she says, hey, I have a better way of spending your $100. I have a better way of spending your $100 than what the algorithm comes up with. So Alice says, look, your algorithm is wrong. I've got a better answer than what comes out of the algorithm. I want to be able to argue that no matter what Alice comes to me with as an alternative to solution, that Alice is full of crap, that there's no possible way that her solution could be better than what comes out of my algorithm, right? So I'm going to argue that there is no possible way that Alice's solution per purchases could yield more value for the budget than my algorithm. Okay. So this is like a general strategy which often works for convincing someone that your greedy algorithm actually works. So So then what I'm going to say is, so if Alice has a better solution, then that solution must then look at the first place, the first time that my algorithm bought something that Alice. So Alice has a solution. Alice's solution is suppose Alice's solution example. Alice's solution is buy 1 bushel of oats, and again, let's say Alice says Alice says 1 bushel of oats. She then doesn't buy the rice. She buys all of the barley and spends the rest on corn, let's say. So she buys 1 bushel of barley and then spends the rest on corn. She claims this is the best possible solution. Okay. This is a bunch of BS. She didn't buy rice. I bought rice. So rice is the first thing that we both bought oats. So rice is the first place where I'm different than Alice. And there has to be a place where I'm different than Alice, because otherwise, if there's no place where mine is different than hers, then we both have the same answer and we're both right. So if Alice is claiming that I'm wrong, then there must be a place where she makes a different decision. She didn't buy the rice. I bought rice. She bought barley second instead. So, okay, so let's see if I can outline this argument. So Alice came to me with an alternative purchasing plan, and she claims that her alternative purchasing plan is the best possible solution. There's some place in this plan, there has to be, I mean, this is just one example, but there has to be some place in the plan where Alice failed to buy something that I bought. So I bought rice, she didn't buy rice, or I bought oats, she didn't buy oats. But at some point, I needed to buy something that she didn't buy. Otherwise, we would just have the same answer and we're both right. So what I'm doing as a thought exercise is Alice says she has the best possible solution, and I say, hey, I bought rice, you didn't buy rice, take the money that Alice spent on something that was not rice and go and buy the thing that I bought. So I'm going to go I'm going to do a thought experiment and move Alice's barley money, or some of Alice's barley money, over to rice and not change anything else about her answer. So
why are you only using part of her barley fund instead of all of it?
Well, so it turns out that their rice is cheap. So there isn't enough rice in the marketplace to go take all $50.
So just as much as you would need to buy all the rice possible, or to buy as much rice as you bought?
So the argument actually works. So all I'm trying to do is refute Alice's claim that she's got the best answer and it's not my answer. So in order to refute her claim, it actually doesn't matter how much barley money we move over to rice. If she spends, even if she just spends like $5 of barley money on rice, she's going to get more value spending that $5 on rice than she would get spending it on barley. Because the reason that I bought the rice is a good value for the buck. So if we take even $1 worth of barley money and spend it on rice, then we are going to improve Alice's solution. And Alice claimed her solution was the best. And so if I can improve Alice's solution at all, I would have refuted her claim and I win. So I'm saying for anytime Alice brings me a solution and claims it's the best, I can find some place where she did something different than my algorithm did. And if I go and like move a little bit of money in her purchase plan, I can come up with I can make her solution better. And so then like her solution can't possibly be the best one. So basically what I'm showing here is that any solution which is not mine that Alice comes up with be the best. So okay, so let's finish this argument, and then this is where we're going. So don't change anything else about Alice's answer. This change will have improved the value of Alice's solution. This contradicts note, we know that moving money from like moving say $1 from a good that I don't buy to a good that I do buy is going to improve the value, because by design, my greedy algorithm is picking the highest value per dollar at each step. So if we take something, so if at a particular point in time, Alice buys something that I didn't buy, we can go and the reason that I didn't buy what Alice bought, the reason I didn't buy, say, like extra barley, is because rice was giving me more value per buck. So it must be the case that if Alice changes a little bit of her spending from something I didn't buy to something I did buy, the things that I buy are more value per dollar. So we must be making the solution better by substituting in the things that I did buy, like oat and rice, for anything that I didn't buy. And so basically what I'm doing here logically is I'm showing that any solution which is not mine, differs from the from my algorithm, any solution that's not mine can't be the best. So if solutions that are not mine can't be the best, then this is logically, this means that the only solution which can be the best is fine. Let me go check the chat. Oh, yeah. So so Eric and Eleanor, for the tie case, yeah, if there's a tie, then if there's a tie, then my answer and Alice's answer could both be the best, or they both could be correct. So like ties aren't a problem for this argument because I'm not articulating that very well. But I'm still correct even if it's a tie. Alice is also a tie. The only way that we can have ties is if there's two items that are both the same value per dollar. If you so I think I'm not articulating this very well. So let's see so with regards to ties, with regards to ties, maybe the right wording she has on optimal solution Yeah, so maybe this is the right way to word it. I appreciate your confusion, Eric, and I think that the argument that I gave here works perfectly well, provided that there's no ties, like provided that you don't have two goods, two commodities that are equally good value per dollar. So maybe with regards to ties, the right wording is something along the lines of, suppose Alice has an optimal solution which is better than mine. I'm going to show that she's wrong. I'm going to show that either her solution is not optimal or it's not better than mine. And then this would tell me that I'm at least tied with whatever the best is. I don't know if that makes any sense, but I think this